Spontaneous versus non-spontaneous. So a spontaneous process occurs without ongoing outside intervention. That's what we mean when we use spontaneous in a chemistry context. So for a simple mechanical system, it's easy to predict spontaneous versus non-spontaneous. I'm looking for something I can drop on the floor. How about this eraser? So I'm holding this eraser out at arm's length. If I let go of it, what's going to happen? It's going to fall. Bang, it fell. That's a spontaneous process. We can predict that, right? If you have something held above a horizontal surface and you stop supporting it, it's going to fall. Do you have to do anything to make it fall? You let go of it and it doesn't stay there. Now, this remote is sitting on the bench and I'm holding it. If I let go of it, is it going to fall? No. Why not? Because there's the bench under it. Yeah. There's no reason for it to fall. But if I held it out here, it would. I'm not going to do that because I want that to keep working. So this guy here, this is a mechanical process. He's pulling down on the rope and lifting this heavy weight. If he lets go of the rope, what's going to happen? The weight's going to fall. So we have experience with things like that. We can predict what's spontaneous and what is non-spontaneous. A non-spontaneous event would be this going up all by itself, right? We see something like that and we're like, whoa, that can't happen. There must be a trick. So for chemical systems, there is nothing obvious like that. And this works for simple mechanical systems. More complicated mechanical systems, it gets more difficult. But we need something similar for chemical systems. We need what's called a chemical potential that will predict what's going to happen, which direction this event is going to go. Because here we have a spontaneous chemical process. If we put sodium chloride, solid sodium chloride, into water, it will dissolve all by itself. We know that from experience, but how would we predict that something like that would happen? So, spontaneity and speed of reaction are not the same thing. You can have something that's thermodynamically spontaneous, it happens on its own, but it can be kinetically slow. So the example in the textbook is the form of carbon known as graphite is more thermodynamically stable than diamonds are. So diamonds are slowly turning into graphite. It's a spontaneous process, but how long does it take? Have you ever seen a diamond turn into graphite? Diamonds are forever, so the saying goes. That happens so slowly that it really doesn't make any difference at all. So spontaneous means it happens, but it doesn't mean that it necessarily happens very quickly. We talked about catalysts at the beginning of the semester. Catalyst increases the rate of a reaction. So if we look at this, here we have reactants and products. The kinetics, which have to do with the intermediate states and the rate or speed of the reaction, that can be altered using a catalyst. If you have a spontaneous reaction, a catalyst will speed it up. If the reaction is non-spontaneous, a catalyst will have no effect on that. So this is showing initial state of lower energy and a final state of higher energy. We would assume that that's going to be a non-spontaneous process, but it's not as simple as that. Another important point here is a non-spontaneous process is not impossible. Think about that guy with the pulley and the weight. The thing moving up, the big weight moving up, is non-spontaneous, but it isn't impossible. It's going to require an external energy supply. The man pulling on the rope is providing energy to raise the weight up. So non-spontaneous processes are definitely possible. They just won't happen on their own.